Welcome to my video lecture based on Electrical Machine 2, paper code PCEE 501. Today's topic is based on our new module, that is Introduction to Fundamentals of Rotating Machines. So various basic principles are maintained by the rotating machines, and based on that the windings has been formed in case of rotating machines. And those fundamentals we will discuss in these lectures of this module series. Myself, Mumum Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandrasur Institute of Technology and Sports Complex. So in this lecture, we will mainly deal with the fundamentals of rotating machine. Let us see what kind of fundamentals we have to maintain for the rotating machines in case of our electrical machines field. So, in case of AC windings, as no commutator is needed in an AC winding, it differs from a DC winding in its configuration. The AC winding need not to be closed one like a DC winding, and hence AC windings are open windings. Remember this one, AC windings are open windings. Since most AC machines are of three-phase type, the windings of all these three phases are identical and spaced 120 electrical degrees apart from each other. The windings are normally connected in star or delta connection, and however, when the three windings are connected in delta, the combination of to form a closed winding, these are the following characteristics need to maintain by the AC windings. First one, usually the number of phases are 3. Second one, the armature windings of synchronous generators and motors are usually connected in star. In the case of three-phase induction motor, both star and delta connected windings may be used. Thirdly, the number of winding circuits in parallel per phase may be one or more than one. Fourthly, the number of coil layers per slot, maybe one or two through the two-layer windings, are much common. And fifth point, the angular spread of consecutive conductors belong to a phase belt, and the arrangement of the end connection of AC windings differs from DC windings. Now single and double layer winding. What do you mean by single layer winding and what is the meaning of double layer winding? In a single layer winding, one coil side occupies one slot completely. Therefore, the number of coils is equal to the half of the number of slots. In a double layer winding, one coil side occupies the upper half of one slot, while the other coil side is placed in the lower half of another slot placed about one pole pitch from the first one. In a single layer winding, the coils are arranged in groups, and the overhang of each group of coil is made to cross the overhang of other groups by adjusting the size and shape of different coil groups. However, in double layer windings, all the coils are identical in shape and size. Hence, a double layer winding results in a cheaper machine. And all synchronous machines and most induction machines of medium and large capacity use double layer winding. That means the maximum machines, AC machines, are generally used double layer winding, and there are some advantages of double layer windings over the single layer winding. First one, simple to manufacture and lower cost of the coils. Secondly, fractional slot and corded winding is possible. Thirdly, lower leakage reactance and hence better performance. And fourthly, better EMF waveform. So these are the main points we have to remember in case of single and double layer windings. Now phase spread. What do you mean by phase spread? When we will call it as phase spread? That we will learn. A group of adjacent slots belonging to any one phase under one pole pair is termed as phase belt. A group of adjacent slots belonging to any one phase under one pole pair is termed as phase belt. The angle subtended by the phase belt is known as phase spread. Let us illustrate this arrangement by considering 2 slots per pole per phase. That is 12 slots per pole pair. The slot angle is obviously 30 degree. We can place the windings of phase R in slot 1 to 4, that of phase Y slots 5 to 8, and that of phase B in slots 9 to 12. Each phase belt has a spread of 120 degrees. The induced EMF of conductors in adjacent slots have a phase difference equal to the slot angle. The resultant EMF per phase is less than the sum of individual conductor EMF. The phase sum of induced EMF in conductors 1 to 4 gives the phase EMF of phase R. The phase sum of the induced EMF in conductors 1 to 4 gives the phase EMF of phase R. In other possible arrangement, the complete winding has been divided in 6 groups, each having spread of 60 degrees. Hence, the conductors in slot 7 and 8 serve as return conductors for slot 1 and 2. And hence the induced conductor EMF in slot 7 and 8 have been marked negative. The phase sum of the conductor EMF gives the phase EMF of phase R, and the magnitude of phase EMF in figure 5.1b is more than the figure 5.1a, and hence the three-phase windings are always designed for 60-degree phase. Now we will see the figures. So this is 3 phases. We have divided R, Y and B. You can see that 1, 2, 3, 4, these slots belongs to R phase. 5, 6, 7, 8, these belongs to Y phase, and 9, 10, 11, 12, these belongs to B phase. That means this is a 12 slotted motor, while we have divided the coil groups in 4. That means 360 divided by 12, that means each slot is 30 degree, and each slot 30 degree, its combination of 4 slots, that means 30 into 4, that is total, gives us the 120 degree spread. In the second part, that is 60 phase spread. So here we can see that R and Y belongs to 1 and 2, then it has been start is B dash, then 4 and 5 belongs to Y, 6, then 7, 8 belongs to R dash, then 9, 10 belongs to B, and 11, 12 belongs to Y dash. In that way we have divided into 60 degree phase spread. Okay. Now full pitch and fractional pitch coils. A two-pole machine which contains one coil housed in stator slots. The coil has a single turn only, and one turn contains 2 conductors. AB and CD are the 2 coil sides, and the peripheral distance between the 2 adjacent poles is called pole pitch. A pole pitch is always equal to 180 electrical degrees. and the coil span is equal to the pole pitch, and the coil span is less than 1 pole pitch. The coil span is distance between the two coil sides of one coil, and the coil span is equal to 180 degree, and the coil span for the next figure, it is less than 180 degree by an angle alpha. The angle alpha is called cording angle and is defined as the angle by which the coil span is less than 180 electrical degrees. That means the total distance between two coil sides of one coil is known as the coil span, and they are generally equal to 180 degree. But if we are making the coil side less than 180 degree, then that will be known as the chorded angle, the angle by which it is less than 180 degree, that is chorded angle. In full pitch coil, the coil sides are 180 electrical degree and apart, or coil span is equal to one pole pitch. And if the coil span is less than 180 degree, it is called short pitch or chorded coil. That is the concept of full pitch and fractional pitch coils. Now, fractional slot windings. In these windings, the number of slot per pole per phase is a fraction. A fractional slot winding may be single layer or double layer, and standard slotting arrangements over a wide range of pole numbers can be used in fractional slot windings. So this is the double layer integral slot windings, part A full pitch coils and part B for short pitch coils. So the total number of slots must be multiplied of 3 so that the windings of 3 phases remain symmetrical. In a double layer fractional slot winding, the arrangement of coil sides is repeated for the bottom layer, and here the coil span is always less than 1 pitch. So we can see that in the first span, that is 1 to 9, are belongs to coil sides of upper layers, and here we have make the coil side in upper layer of RR, do number 2, that is also belongs to RR, and number 3, that is also belongs to 3 RR, and 4 5 6 belongs to B dash B dash, 7 8 9 belongs to Y and Y, and 10 11 12 belongs to R dash, 13 14 15 belongs to B, and Y 16 17 18 belongs to Y dash. So we can see that the pair of R and R dash are made equal numbers, B and B dash made equal numbers, and Y and Y dash belongs to equal numbers. That means each coils are divided into 2 slots. That means it is double layered. Here we can place two coils in 2 layers. 2 coils for R slot, 2 coils for Y slot, like that. We can put the 2 coils in 2 layers. Okay. Now, advantage of distributed winding and fractional pitch winding. The advantage of distributed windings are: point 1, reduction of harmonic effect. Advantages of distributed winding and fractional pitch winding. The advantages of distributed winding are: reduction of harmonic effects in the EMF signal. Second advantage, adding mechanical strength to the windings. Third advantage, full utilization of armature iron and copper. The advantages of fractional pitch windings are: 1. Reduction of harmonics in the generated EMF signal. Secondly, the reduction of copper for overhanging, which results in reduction in cost of the machine. Thirdly, the reduction of magnetic losses due to elimination of high frequency harmonics. The only disadvantage of fractional pitch winding is that the terminal voltage is a bit less than that of the full pitch coils. So we have made advantages of distributed winding and fractional pitch windings in separate manners. The concept of electrical degree and mechanical degree. Let us consider a two-pole machine as per shown in the figure. Two-pole machine with single rotor coil, and it's second B showing that EMF variation with omega t for two-pole machines. These are the two poles actually, North Pole and this one is the South Pole. And this is the generated EMF for two-pole machine. We assume one rotor rotating at uniform angular speed. When the rotor coil is at the position 1, the EMF in the coil is 0. Though the coil, but the rate of change of the flux is minimum. Let us consider that 1 is the initial position of the rotor coil which is rotating in the clockwise direction, and after 90-degree revolution it reaches the position 2 where the EMF in the coil becomes maximum. Though the flux cutting the coil is minimum at this position, but the rate of change of flux is maximum. When the coil reaches in the position 3, the EMF is 0, and at position 4 the EMF is maximum. But direction of the EMF is opposite to that of the position 2. Thus, when the rotor completes its one revolution and returns to the position 1, the EMF in the coil is again 0, and hence one complete revolution of the rotor coil and one full cycle of the coil EMF is generated. Now let us consider for a 4-pole machine as shown in the figure 5.6. It is assumed that the rotor coil starts from the initial position 1 where the EMF is 0, and when it is at position 2 the EMF is maximum, and again in position 3 EMF is 0, and at the position 4 the EMF is maximum, but in again direction opposite to that at position 1, hence the EMF considered negative maximum. Again at position 5 the EMF is 0. So in that way it is moving. It is 0, then it is goes to maximum, then again 0, then it's negative maximum, then again 0. In that way the EMF is total moving. Thus one full cycle of EMF is generated while the rotor coil completes only one half of the revolution by moving from position 1 to 5. In a similar way, when the rotor coil completes full revolution, another full cycle of EMF will be generated. Hence, two cycles of EMF, that is 720 degree, is generated in one revolution of 360 mechanical degrees for 4-pole machine. 720 electrical degree is equals to 2, and 720 electrical degrees equals to P by 2, 360 mechanical degrees. That means theta electrical equals to P by 2 theta mechanical, where P is the number of poles of the machine. In other words, in a p-pole machine, in one revolution of the rotor, P by 2 cycles of EMF is generated. So that's all about today's lectures on rotating machine fundamentals. In my next lecture, again, we will continue about this topic. And this total lecture I have taken from the book of Abhijit Chakraborty of Electrical Machines. And thank you all for listening my lecture.